So hello everyone. So today we shall continue our discussion from the last lecture where we have been discussing about the frequency response characteristics. So today we shall see the impulse response for rational system functions. Okay. So in the previous lectures we had seen that how that given an impulse response of the system, how you can, or in the frequency domain, how you can compute the impulse response in the time domain. So there were a couple of methods we had discussed, but mostly we relied on the partial fraction method, where the rational system function was expressed as the summation of the multiple order functions, and finally we used the inverse Fourier transform or the Z transform to write their time domain representation. So if you recall that any rational function of Z inverse with only first order poles can be expressed as h of z as the first term or is equal to 0 to m minus n. So m and n are the order of the difference equations on the left hand side and the right hand side. So the first term is br z to the power minus r, where there is no rational term, plus the rational term of which is composed of the first order poles. So it is expressed as ak by 1 minus dk z inverse, right? Now if your h of z has a multiple first order poles, then in that case you would have uh, the same term. Let me copy this. So for multiple first order poles, you would have k is equal to 1 and k is not equal to I, plus you have some term in addition to the multiple order poles, which is from m equal 1 to s for some cn 1 minus di z inverse to the power n. So the first expression is for the rational functions of z inverse with only first order poles, while the second expression is for if your edge of there has a multiple order poles. Right? But most of the time we would be analyzing this rational function, because whatever the analysis we shall carry out for the first rational function would directly be applicable to the second expression. Okay. Now carrying forward with the first expression, if the system is assumed to be causal system, then we had seen that the ROC would be outside of all of the poles, and it follows that your h of n, this is with respect to the first expression, can be expressed as summation of r is equal to 0 to m minus n dr impulse function of n minus r plus the second summation, which is k1 to n ak dk to the power n and u1. So you can express it this way. Note that this first term would only appear, that is only if you have m is greater than or equal to n, otherwise there won't be the first term. So saying this impulse response representation, there are basically two classes in which we would be interested of. These two classes are of the system of this generic impulse response. So the first class is, let's write it, two classes of systems. So the first one, we have at least one non-zero pole of h of z is not cancelled by a zero. In that case, your h of n will have at least one term of the form, and that form is ak dk to the power n and u. Okay? The other implication is that your h of n will not be of finite length, will not be of finite length. So those systems we call them the IIR system, infinite impulse response system. Okay, so this is the first class. The second class, of course, is the FIR system, finite impulse response system. So for those, that class, your h of z has no poles except at z is equal to 0. That is, your n is equal to 0 in that difference equation, what we had seen earlier. Let me write it for your reference. For k is equal to 0 to n, ak y n minus k is equal to summation k is equal to 0 to n bk of x n minus k. Okay, h of z has no poles except at z is equal to 0. So in that case, partial fraction is not possible, which meaning to say that it is simply, your h of z would simply a polynomial of z inverse. That is, it can be expressed as h of z summation from k is equal to 0 to n bk z minus k. Obviously, it is pre-assumed that your a naught is equal to 1. So for so for this h of z, you have your h of n given by k is equal to 0 to n bk del n minus k, which can also be equivalently represented as bn for n lying between 0 to m and it's 0 otherwise. Okay, so you see that the infinite impulse response, what we had seen generically of the above class, will be finite in length because of this h of n. That's why the second class is your finite impulse response system. Now there are a couple of terms which we had studied earlier about the magnitude response, the phase response, the principal value of the angle, and the group delay. Now we can see closely then for a rational system function in general. So we write frequency response of rational system functions. Okay. So let's quickly write the expression. What we want to see, that h of g omega is expressed as the ratio of two polynomials. In the numerator we have k is equal to 0 to n and bk e to the power minus j omega k, while in the denominator we have k is equal to 0 to n ak e to the power minus j omega k. If you recall, we had also expressed in terms of by using the multiplication operator, where it's the multiplications of various poles and zeros. So this can also be equivalently written as h of e to the power j omega b naught by a naught for k1 to m 1 minus ck e to the power minus j omega, and in the denominator we have k equal 1 to n 1 minus dk e to the power minus j omega. Okay, of course, the magnitude response is computed by taking the modulus of it, which would be this one, of course. Right? So if you want to compute the magnitude squared function, so it would be simply h of e to the power j omega, the response, which you can express as e to the power j omega and its complex conjugate as e to the power j omega. So you can substitute h of e to the power j omega and its complex conjugate, and you can multiply them to obtain the magnitude squared function. So it would be a long expression, but you can see by yourself that how it looks like. So the another important thing is the gain in dB. This would be useful when you analyze the frequency response and the magnitude response and the phase response on the body plot. So generally we the use to plot them on the logarithmic scale so that we can cover high frequencies as well. So the gain in dB is computed as by taking the 20 times log base 10 of the magnitude function power j omega. So for the above expression, it would be 20 log base 10 b naught by a naught. And by using the logarithmic property, it can be written as summation from k is equal to 1 to m 20 log base 10 of the numerator magnitude 1 minus ck e to the power minus j omega minus k is equal to 1 to n 20 log base 10 of 1 minus dk e to the power minus j omega. Okay, this would be your gain in decibels. While the phase response, we use this argument of h of e to the power j omega as argument of b naught by a naught plus summation of k is equal to 1 to n argument of 1 minus ck e to the power minus j omega minus, because minus we are having because we are it's a denominator polynomial which corresponds to the pole, while the numerator polynomial corresponds to the zeros. So k is equal to 1 to n argument of 1 minus dk e to the power minus j omega. Right? So note that this argument we had discussed already, that this is a continuous phase which is also unwrapped. Unwrapped phase, because when we compute the the its principal value, it should be lie between minus pi and pi, while the group delay, it's the differentiation of this argument. So if I write group delay of this function h of e to the power j omega, it would be the first part, the first term would be 0, of course, because it's not a function of omega. So it would be k is equal to 1 to n, since it would be the minus of derivative. Yeah, minus of derivative of the argument function. So it is given by k is equal to 1 to n d by d omega of 1 minus dk e to the power minus j omega. And here we will have the negative sign for this one. It would be k is equal to 1 to m d by d omega of argument of 1 minus ck e to the power minus j omega. Okay. By taking these derivatives of these functions, there is one equivalent expression also where you don't see this derivative operator explicitly, You can also compute by yourself, which is given by as summation from k is equal to 1 to n mod dk square minus real part of this dk e to the power minus j omega divided by 1 plus dk mod square minus twice of real part of dk e to the power minus j omega minus summation from k1 to n. You have mod ck square minus real part of ck e to the power minus j omega divided by 1 plus mod ck square minus twice real part of ck e to the power minus j omega. So this is just for your reference. You don't need to remember these formulas, but you can compute these formula by yourself as well once you are given the rational function of the system, right? Likewise, so far we had the discussion of the generic rational system function, but since we are interested in the response of the first order system because it gives us more insights about the properties in the magnitude response and the phase response. So initially we shall see for the first order system about all these three terminologies we have introduced for the generic rational system function, and then you can extend it to the multiple order systems as well. So frequency response of first order system. So for the first order system, we would be mainly interested in properties of single factor of the form. By using the polar coordinates, you can express it as 1 minus r of e to the power j theta e to the power minus j omega, where this r is the radius and theta is the angle of either pole or 0 in the z plane. Okay, so we shall see both analysis of this first single factor both in the on the body plot and also on the vector plot. So if we apply the above formula of computing the gain in decibels, it would be given as gain in decibels. So you would have plus and minus. Okay, so the plus, okay, let me write the expression first and then we shall discuss. So 20 log base 10 of 1 minus r e to the power j theta and e to the power minus j omega, which you can write as equivalent to plus minus 10 log base 10 for 1 plus r square minus 2r cos omega minus theta. Okay, so here we have not used the plus minus terminology in the usual sense, but we wrote plus oblique minus because positive sign in the above expression corresponds to a 0. If this factor is appearing on the numerator, then we would use positive sign. We would use negative if this factor is appearing as a pole in the, that is to say, in the denominator of the rational function. Okay. Next, the principal value, which is again plus oblique minus, and here we use the capital arguments of this function 1 minus r e to the power j theta and e to the power minus j omega, which can be computed as plus and minus using the arc tangent subroutine arctan of r sine omega minus theta and 1 minus r cos omega minus theta. Okay, the group delay, you can also use this principal value function by differentiating this principal value function except at the discontinuities. Okay, so this group delay is given by again plus or minus of group delay of the above vector as plus or minus r square minus r cos omega minus theta and 1 plus r square minus 2r cos omega minus theta, right? Or equivalently you can express this as a square of the magnitude function plus minus r square in r cos omega minus theta, and this square of the magnitude function is used in the denominator as the 1 minus r e to the power j theta and e to the power minus j omega modulus square. So this is the square of the magnitude function. Okay, so now having seen all these expressions, now we shall try to visualize them on the logarithmic, on the separately the frequency response and the magnitude and the phase response. So this, let me unzoom it. So here you see three plots. The first plot is for the gain in dB, where omega for the moment we have kept at the uniform scale, not on the logarithmic scale. The second one is the radian, and the second one is the group delay. Okay, so here we have kept the radius of that first order vector same. So here we have used r is equal to 0.9, but here we are using three different values of theta. Theta is equal to 0, theta is equal to pi by 2, and theta is equal to pi, so that we can see that what happens at those particular frequencies. Okay, so the first important point to notice that the phase which is on the second plot, so if I see the solid line is for theta is equal to 0, so the phase is 0 at omega is equal to theta. So this is 0 at omega is equal to theta, and that for fixed r the function simply shift with theta. So here we have, when we use the plot theta is equal to 0, the phase is 0. When you have theta is equal to pi by 2, which is a dashed dotted line, then it is also 0 at theta is equal, at omega is equal to pi by 2, and for the dashed line it is 0 at omega is equal to theta, which is equal to pi. So the phase is 0 at omega is equal to theta. Now the figure C shows the group delay function for the expression we had seen earlier. So you would notice that the high positive slope of the phase around omega is equal to theta, which corresponds to a large negative peak in the group delay function at omega is equal to theta, right? So yeah, this is for the dashed dotted line, this is for the solid line, and this is of course for the solid line, which is theta is equal to 0. So here you see the large peaks in the group delay function at omega is equal to theta. Okay, another uh, in the A figure, you see the plot of the gain, magnitude gain as a function of omega over one period for omega lying between 0 to pi. So here you would notice the dip in the magnitude response at omega is equal to theta. Here, here, and of course here. Of course, it would repeat after 2 pi. Okay. So this plot shows the where we have plotted the responses in the frequency domain for various values of theta, but keeping the radius 0.9 as fixed. But now if we fix the theta, then this is how the plots appears for values of r changing from 0.5 to 1. Note that in the figure C, which is the group delay function, we have not used for r is equal to 1. So there are only 3 subplots in the figure C for r 0.5 to 0.9, while in the first two plots A and B, you see for r 0.5 to 1. Okay, so the log magnitude function in the figure A, so theta, here we have fixed the theta is equal to pi, because it is pretty much straightforward, because here you see the dip in the log magnitude function, so it dips more sharply as r becomes closer to 1. Okay, indeed the magnitude in the dB approaches minus infinity at omega is equal to theta as r approaches to 1, right? Now the second plot is about the phase function, which has a positive slope around omega is equal to theta, since theta is equal to pi. So here you see the positive uh, phase for omega is equal to theta, which becomes infinite in principle as r approaches to 1 in comparison to other r's from 0.5 to 0.9. So it is straightforward that for r is equal to 1, the phase function is discontinuous with the jump of pi radians at omega is equal to theta. And away from omega is equal to theta, the slope of the phase function is of course negative. Now talking about the group delay, which is plotted in the C figure, the group delay is the negative of the slope of the phase curve. So the group delay is negative around omega is equal to theta, and it's dipped sharply as r approaches to 1, becoming an impulse. That's why we have not plotted the the group delay for r is equal to 1, because it would approach. It is like an impulse function when r is equal to 1. Okay, and as we move away from omega is equal to theta, the group delay becomes positive and relatively flat. So these are a couple of analyses which would be helpful when we will just when we will design the frequency selective filters. Okay, now in the vector plot there are some more analysis. So this is how this vector plot looks like. So for a first order system function of the form h of z is equal to 1 minus r e to the power j theta and z inverse, this is for this particular scenario which can be expressed as z minus r e to the power j theta and z for r less than 1. Okay, so here you see clearly that there is a pole, there is a zero which is having a vector of length r from the origin, and it is rotated in the anti-clockwise at theta, while there is a pole at z is equal to 0. So this is for this particular scenario. Let's say for the 0 we denote it by some vector v2, and this is a moving vector v1 at a angle of omega. Okay, So by using the vector calculation, you can compute this vector v3, which is nothing but v3 is equal to v1 minus v2. Okay, so each pole and zero vector, what you will see in the rational function, you can represent them by a vector in the z plane, from the pole or zero to a point on the unit circle. So this is the imaginary axis, this is the real axis, and this is your z plane, right? So we'll talk about this phi 3 which you are seeing on the plot in next couple of seconds. So vector v1 is basically denotes the complex number e to the power j omega. Since the radius r is equal to 1, it's inside the unit circle. The vector v2 denotes r times e to the power j theta, and vector v3 is the difference of these two, that is vector v3 is e to the power j omega minus r of e to the power j theta, which is basically v1 minus v2. Okay, so in terms of these vectors, the magnitude of the complex number, uh, if I substitute z as e to the power j omega minus r e to the power j theta e to the power j omega. So the magnitude of the complex number, this one, is the ratio of the magnitudes of the vector v3 and v1 basically, because then in the numerator you have v3 vector and in the denominator you have v1 vector. So computing the magnitude of this one would be equal to your v3 over v1, and since v1, the magnitude of v1 is equal to 1 since it's in the unit circle, so it would be equivalent to mod of v3, and the corresponding phases, if you compute as angle of 1 minus r e to the power j theta and e to the power minus j omega, it would be equal to angle of the numerator polynomial, which is e to the power j omega minus r e to the power j theta, minus the denominator polynomial, which is angle of e to the power j omega. And since the first term is of the vector v3, so I can write it as angle of v3 minus angle of v1. And angle of v3, this vector, from the horizontal axis, it is in the anti-clockwise direction, is phi 3. Okay, and for v1, let's say it is some phi 1, although we know it is omega, so I can write it as phi 3 minus phi 1, where phi 3 we had seen on the vector plot that how it is computed, but phi 1 is nothing but your omega. Okay, it is from this horizontal axis, it is this one omega, right? Therefore the contribution of a single factor, this one 1 minus r e to the power j theta z inverse, to the magnitude function at frequency omega is the length of the vector v3 from the 0 to the point z is equal to e to the power j omega on the unit circle. So note that this vector has a minimum length, this vector v3 of the minimum length, when you have omega is equal to theta, right? And this accounts for the sharp dip in the magnitude function at omega is equal to theta in this figure, what we had seen earlier in the magnitude response. Okay, because the vector has a minimum length when omega is equal to theta. So we also know that the vector v1 from the pole at z is equal to 0 to z is equal to e to the power j omega always has unit length. Thus, it does not have any effect on the magnitude response. Okay, so these are some plots which you can use to do the analysis of the rational system function, and we shall continue with this discussion for other types of system. So for example, all pass system and minimum phase system, the term which we had seen in the last lecture. Now in the next lecture we shall see, after all these discussion and all these plots, that what is the geometrical interpretation of those minimum phase system. Okay, so this discussion is for the single factor of the form this, which may appear in the numerator or the denominator. But if you have multiple poles and zeros, you can carry out the same analysis, and you can relate the vector analysis to their frequency response, that when they will see the dip, when it would be zero, when in the group delay you have a maximum dip as well. Okay, for FIR system and for IIR systems as well, once you divide them into two different classes. Okay, thank you.